In this experiment, I investigated a falling object's motion and its relation to Newton's second law. Newton's second law states that the final velocity is equal to the initial velocity plus the net force divided by mass multiplied by time. In the falling object's case, the net force is equal to the force of the gravity plus the force of drag. The force of gravity is equal to the mass multiplied by the gravitational pull of the Earth, which is about 9.8 meters per second squared. This force is in the downward direction as the gravitational force pulls down on the basketball. The force of drag is equal to the instantaneous velocity at a given moment squared. This force opposes the downward force of gravity and pushes upwards. In this lab, I created a computational model for the basketball's motion with and without drag in VPython. I then compared these models to my experimental data. This is the code I used to create the model for the ball falling without drag. Here I changed the mass from 1 to 0.623 kilograms. And here I set the initial position to 0, and here the initial velocity to 0. I set g equal to negative 9.8 meters per second squared, and this will become important later. Here I set all the conditions that were necessary so that the conditions were the same here as they were in the experimental model, as in the experimental data. Here I set the Fg, which is the force of gravity, equal to the mass of the ball, times gravity, the gravitational constant, multiplied by j hat. And also in this model, the one without drag, the net force is equal to the gravitational force. Here, this essentially updates the ball's velocity per 0.001 seconds. It says that it is equal to the initial velocity plus the net force of the ball divided by mass multiplied by time. This right here is Newton's second law, and this is what I used to create the model. This is the underlying concept that I used to create the model. This updates the position of the ball every 0.001 seconds. And when I run it, this is the graph that appears. This is the code I used to create the model with drag. It is essentially the same model, all except for one essentially different thing. Here in the net force, the net force is not only equal to the gravitational force, but it's also equal to the gravitational force plus the drag force. And in this case, the drag force is equal to the magnitude of the ball's velocity squared. And so another thing I also did in this model was put the arrows. To do this, I had to create an arrow scale and make the arrow's position start at the ball's position, and the axis of the arrows to scale according to the net force, or the gravitational force and the drag force. And when I run this one, it looks like this. Here you can see the arrows. The drag force increases as the ball moves downwards, while the gravitational force stays constant. And the graph looks essentially the same. This is a comparison of all the graphs put together and plotted on the same graph. Here in blue, you can see the model with no drag. As you can see, it drops much quicker and faster than the experimental model and the model with drag. This is due to the fact that, of course, there is no drag. Drag opposes the gravitational force and thus slows the ball down, whereas in this model, it continuously accelerates downward. In yellow, you can see the model with drag, and as you can see, it is closer to the experimental data. However, it is still off, and this is due to the fact that the drag equation is not exact. And in green, you can see the experimental data, which pretty much falls right in between. Here in this set of code, I've made only one crucial adjustment to the drag code. Here I put the initial velocity to a -5 downwards velocity. As a result, when I run this code, the graph looks slightly different because there's a higher initial velocity and thus the ball is going down faster at first. And when I plotted this in Logger Pro against the original drag velocity model, you can see that both are approaching the same terminal velocity. As a result, in reference to the what if question, the terminal velocity does not change if your initial velocity is thrown faster or not. It stays the same.